An industrial plant has the hypothesis that mu is equal to 85. The question reads, the average daily output of an industrial plant is scheduled to be 85 units. 25 days are selected at random and the output is observed for each day from this sample of size 25. The average output is calculated to be 81, and the standard deviation is 8 units. At 5% level, test whether the actual output is different from that schedule. And so, as you know from doing problem solving, you start off with the given information. So we have a sample size of 25. We have a sample mean of 81, a sample standard deviation of 8. We're going to let alpha be 0.05. That's the level of the test. And because the statement of the question said it's supposed to be 85, it should be either above or below. If you make too much, that's a bad thing. If you make too little, that's a bad thing. So it's a two-tailed test. So the level of the test is 0.05. And we're going to divide that between two tails. And the null hypothesis is that the mean level of production is 85. So the t-statistic for 24 degrees of freedom with 0.025 in the tail is minus 2.064 and plus 2.064. That cuts off a total of 5%, 2.5% in each tail. And our observed t-statistic is the sample mean minus the mean under the null hypothesis divided by the standard error of our estimator. So the observed t is minus 2.5, and that lies outside the critical value, lies outside the median segment. It's in the lower tail. Okay. So we reject the null hypothesis. In the fourth question, you're given a quadratic form. The first step was to find the roots. And one of the things that we know is that ax minus lambda x should be equal to 0, where lambda is a characteristic root of a. And so we can factor that as a minus lambda times the corresponding identity matrix post-multiplied by x. That's supposed to be 0. If there's going to be a non-trivial solution, then it must be the case that the matrix in square brackets is not a full rank. That is to say, the determinant of a minus lambda I, which determinant, must be 0. So I skipped that intermediate part, and I just subtracted the lambda off from the main diagonal. And take the determinant of the determinant of that two-dimensional matrix is 16 minus 10 lambda plus lambda squared. So of course there are two roots. There are two roots that will make that determinant 0. And you could use it. You could figure it out using the infamous quadratic formula, which you all learned in 8th grade. And I know you learned it in 8th grade because my daughter has finished 8th grade. And she knows it. And by the way, in case you're wondering whether or not it's really worth remembering this stuff and bothering to buy MathCAD and learning it, or Mathematica, yesterday my daughter was in 9th grade and was studying for a math test today, and they were already figuring out how to solve the closed form representation of an infinite series in 9th grade. They're already responsible for deriving the binomial theorem in 9th grade. When my son went to university as a freshman, the presumption was that they already knew mathematics. It wasn't that they were going to learn it while they were students, and this was 7 years ago, 2001. So when your students get to you, you better make sure you know all the stuff that they know. So those are the two roots, 8 and 2. The next step is to find the latent vectors. That is, a characteristic vector or eigenvector that corresponds to each of the two roots. So again, we could go back to the equation that we started with before and ask what x, for the given lambda, what x makes that equation true? Well, as many of you discovered, the vector that does that is not necessarily unique unless you impose a restriction on it. So once you've found a characteristic vector that would work, that you alleged was a characteristic vector, but it had a problem in that it wasn't unique. So how do you get them to be unique? It requires that they have unique length. So from this we get the two equations. I just simplified the previous line there. And we get the two equations, and we impose the restriction that the terms in the first characteristic vector is such that the sum of their squares is 1. And you can rewrite because that's not a proper function, you can rewrite it in one of two ways. And then on substitution, you get the solution for the two entries in the first characteristic vector. So the way to read the answer key is to read it such that you go down that column to get one answer, and you go down that column to get the other answer. I was trying to save space, so it wouldn't take so long to scroll through things and see them. And then you have to go back and do the other one. For the other latent vector, we also get two equations. So the two equations can be reduced to the given. The first one up here. For these, I solved the system of equations by hand, which gets pretty tedious. And so for the second ones, I used some built-in functions in MathCAD. I didn't feel like going through all the arithmetic all over again. And MathCAD has a really neat thing in it called the solve block, where you give it a system of logical identities, and it will find the unknowns that make all the identities true. So the three equations that we had the two equations from the determinantal equation and the restriction, and we could tell MathCAD to find those two solutions to that system of three equations. So the other characteristic vector was minus 0.577 and 0.1816. Oh, and by the way, this solve block notation, once you get really good at it, at setting them up appropriately, you can solve, for example, systems of differential equations for them. So one of the things that you guys who are financial engineers, one of the things that you have encountered is that, for example, when you're valuing a defaultable bond, you get a system of differential equations, one of which is a Riccati equation. And so-called Riccati equations don't have closed-form solutions. You have to solve them numerically. And so this is a way to do that. This MathCAD mathematical stuff is really powerful. So it's worth learning.